But it was quite a, I mean, it was, the power outage happened well before the explosion. I mean, the big fire. Oh, so somebody was down there fixing it and it exploded? Wow. Anyway, I thought, before class starts, I'm just curious if any of you know who Corey was. I mean, we're in Corey Hall. So in the past, I had given a talk to engineering students to ask them, so here are the choices. Who do you think this hall is named for? Definitely C. Well, obviously, yeah. Professor Corey, so the reason I mention it is because if you look at the history of our department, Professor Corey, he actually did electric power research, right? So basically, Professor Power did research here in Corey Hall on electric power, and he actually, as you notice here, because he was doing that electrical research, equipment research, he actually ended up supplying power to the entire campus. Okay, so basically, he eventually became dean, and so on. But anyway, that's historically who our hall here is named for. Okay? The person who was responsible for electrifying our campus. And this building, yeah, is 60-something years old, but it's being remodeled slowly. Anyway, okay, so that's some trivia. Announcement. It's noted on the syllabus at the beginning of class, but the second quiz is, from now on, you'll have a quiz every 2 weeks. Second quiz will be next Tuesday in class. Again, it'll be 25 minutes, 25 points. It will cover the material pretty much on quasi-Fermi levels, generation recombination, the material since homework 4, but I will not cover p-n junctions. Okay, so p-n junctions will be saved for quiz number 3. All right, and as was the case for the first quiz, it will be closed book, but now you can add one more page of your notes. Right? So you can have the notes from the last time and add one more page. And no, you should not need any calculators or any other electronic device. Okay. So. So the quiz will cover Schottky contacts. And so the reader gave us feedback today that a lot of people didn't draw the energy band diagrams for the Schottky contacts accurately. So I just wanted to remind you that if it was not, maybe we didn't explicitly state it yet, but if you're applying a bias voltage, okay, then you're applying electric field. The system is not in equilibrium if you have a forward bias or a reverse bias. So the Fermi level is not going to be the same on the left and the right side. It's not going to be the same in the metal as in the bulk of the silicon. Okay, so here's an example from the homework solution for a metal contact to p-type silicon. Okay, and the Fermi level in the neutral region of the silicon is close to the valence band edge. But notice that the Fermi level in the silicon away from the junction is not lined up with the Fermi level in the metal, right? So you can tell by looking at this energy band diagram right away that this is not a contact in thermal equilibrium because the Fermi levels are split. And the distance of that split, the amount of that split is directly proportional to the applied bias. Okay? So that's just, fundamentally, you should be able to recognize if a junction is not in equilibrium. So just look for the Fermi level being, either flat, which is in equilibrium, or not flat, in which case it is not in equilibrium. Now, looking at this energy band diagram, you should also be able to tell if it's forward bias or reverse bias. Now, remember, forward bias means that you're reducing the barrier to make it easier for carriers to flow into the metal, and so current flows easily. So that's the direction of bias, polarity of bias that allows easy current flow. If you're applying a reverse bias, then the total band bending, the total potential barrier that the majority carriers see is going to increase. So you have hardly any current flow across the junction. Okay, so looking at this example, is this N-type or P-type silicon? It's P-type. So the carriers that you're aware, that you care about are holes. So looking at this energy band diagram, is it easier or harder for holes to flow across the junction with this shift in the Fermi level? It's easier. So this is forward bias. Okay? So you should be able to recognize, do this qualitative analysis for both contacts to N-type and P-type silicon on the quiz. And the total amount of band bending is really the voltage drop in the silicon. And the more voltage you need to drop in the silicon, the wider the depletion region has to be to have enough charge, charge density to support the electric field and the voltage drop. Okay? So these are qualitative things that you should know for the next quiz. Right. Any sort of leftover general questions about metal semiconductor contacts? Okay, so Fermi levels, quasi-Fermi levels, also apparently people didn't quite get. Okay, so a quasi-Fermi level. Okay, so if you're not looking at thermal equilibrium, then you cannot draw a single Fermi level to represent the concentration of electrons and holes. Okay, because NP. Okay, in equilibrium, the Pn product equals what? Ni squared. So as you increase N, you have to decrease P. And so the same Fermi level can represent both N and P, because as you, let's say, move the Fermi level up, you increase N, but you decrease P, right? Okay, so now if you're shining light on a semiconductor or you're applying electric field, it's no longer in equilibrium. P times N does not have to be equal to Ni squared, so you cannot draw a single Fermi level. So if you have a semiconductor in non-equilibrium, you have to draw two Fermi levels, one to represent the concentration of electrons, the other one to represent the concentration of holes. Okay, and apparently on the homeworks, you guys, a lot of you still drew one Fermi level. So just review the answers to the homework problems so you can be prepared for that question on the quiz. Okay. All right. Or we can answer questions during the office hours. Happy to do that. Okay, so today we're going to finish, we're going to look at the current as a function of voltage for a p-n junction diode. So at the end of the last lecture, we reviewed the impact of, or we sort of started looking at the impact of an applied voltage for a p-n junction. So again, in equilibrium, at the very top here, there's a single Fermi level. So that tells you that the applied bias is 0. Okay, and just to remind you, in an energy p-n junction band diagram, the lower side is always the n-type side. Okay, because we can never apply a bias to overcome that built-in potential, like to make it even the opposite polarity. Okay, so looking at an energy band diagram for a p-n junction, you know the side with the lower bands is always the n-type side. Okay, so the Fermi level is, if it's a single Fermi level, then you know it's in equilibrium. If the Fermi levels are split, like in the middle case, you know that a voltage is applied, and the amount of voltage applied is going to be proportional to the amount that's split. So again, in forward bias, this total potential barrier to electrons diffusing to the left and holes diffusing to the right is decreased. Okay, make it easier for carriers to diffuse across. Under reverse bias at the bottom here, the total amount of energy band bending, the total voltage drop is greater. So it's going to be harder for electrons to diffuse due to concentration gradients to the left. And also it's harder for holes to diffuse to the right due to the concentration gradient. Okay, so remember, holes tend to want to diffuse. Diffusion is driven by concentration gradients. So on the left, you have a lot of holes, and on the right, you have few holes. So holes will tend to want to diffuse to the right. And you have the opposite case for the electrons. Okay. Okay, so one thing I didn't highlight, but hopefully it's obvious, that the total voltage dropped in the silicon is now going to be the VBI, the built-in potential, minus the applied bias. Okay, so for a p-n junction diode, the polarity is always defined like this, where the direction of easy current flow is for VA greater than 0. Okay, so this is forward, and this is reverse. Okay, so the equation that we had derived for the depletion width, remember, it's just going to be the square root of 2 times the permittivity times the total voltage drop in a silicon. So in equilibrium, of course, this is just VBI. But now with an applied bias, to make it more general, it's VBI minus VA. And then it depends on the doping concentrations, 1 over Na plus 1 over Nd. But typically, one of these is going to be much larger. One of these doping terms is going to be much larger. You just retain the term that corresponds to the more lightly doped side. Okay. Okay, so that's just to explain why in the summary we have, VBI minus VA here, and in the one-sided junction, same thing. Okay. Now in some classes for homework, it might ask you to rederive the equations for the depletion width, assuming now that the dopant concentration is not constant on each side, but it's a linear function of distance. But essentially, you just go through the same process of integrating the charge density profile to get the electric. Oops, sorry. This is just Q ND on the right and minus Q NA on the left. Okay, then you integrate the charge density profile to get the electric field distribution, and then you integrate again to get the electric potential distribution versus distance. So if you have a linearly doped kind of graded junction, PN junction, then you end up with third order kind of curve for the electrostatic potential. But that's just sort of a mathematical exercise. Hopefully qualitatively you can see that this is the case. What was the question? Okay, so the question is, okay, so typically we start with a silicon that's p-type dope, and we might form a n-type, n plus region at the surface and form an n plus p junction. So the net doping concentration profile, well, it could look like this, but more. You're right. That's right. So basically, what we're assuming in this class, just to make the equations easier, is that yes, we know in reality there's going to be probably both n-type and p-type dopants on one side of the junction, but all we care about is the net doping concentration. So we're just going to call ND the net donor dopant concentration on the n side and NA the net. So that's just to make the equations easier. But in reality, as we mentioned last time, so what it means is that we're ignoring the fact that the mobility is actually going to be a little bit worse than what we expect it to be, because there are really more dopants than we're idealizing. Yeah. Okay. Okay, so let's talk about current flow then in a p-n junction diode today. Oops. Wrong. Okay. So again, energy band diagrams under equilibrium, forward bias, and reverse bias. Okay, so hopefully you can recognize now if it's a small barrier to carrier diffusion, then it's forward bias. And if it's a large barrier, then it's reverse bias. Okay, so let's review. When you bring an N and P-type material, these materials into contact, there's going to be a concentration gradient, big change in hole concentration across the junction, big change in electron concentration across the junction. So there's going to be diffusion. So carriers will diffuse. The majority carriers are going to diffuse across the junction, but then they leave behind the depletion regions. And because of the charge in the depletion regions, you build up an electric field. And that electric field establishes an electrostatic potential that counteracts diffusion. So in equilibrium, so this is going to website. In equilibrium, you have, in principle, due to the concentration gradient, you have majority carriers diffusing across the junction, right? Because they're going to the side that has lower concentration. But because of the electric field, you'll also have drift of carriers across the junction. And at equilibrium, the rate of carrier diffusion matches the rate of carrier drift for both electrons and holes across the junction. Okay, so let's look at that a little bit more closely. Oops, not like that, but like this. Okay, so I think the key thing here is that we're talking about majority carriers that diffuse across, okay? And then drift, as depicted here, is due to minority carriers, right? So minority carriers, let's say, so on the N side, on the right, holes, that happen to wander into the depletion region will see an electric field. And the electric field is pointing to the left here. So the hole will be accelerated to the left. Okay, the holes will go to the left. Electrons, on the other hand, on the p side, they're minority carriers, right? So on the p side, you have electrons that are minority carriers that if they wander into the depletion region, they'll be swept to the right. Okay, so remember, electrons like to go downhill, holes like to drift uphill, right, float uphill. So basically, that's the picture at equilibrium. Now, if you apply a bias, you're going to disturb this balance. If you apply a forward bias, you're going to allow the majority carrier diffusion across the junction to dominate. If you apply a reverse bias, it's going to be the drift current that dominates, okay? Because you're exponentially changing the diffusion current by changing the potential barrier height. Okay, so can somebody remind me, why does the concentration of carriers that can diffuse across a junction, why does that change exponentially with the barrier height? Right, remember the first homework or the first quiz, I mean the exponential tail, right? There's an exponentially decreasing density of electrons at higher and higher energies. And same thing, so carriers with higher and higher kinetic energies, there's exponentially fewer of them. So if you lower the potential barrier, you're exponentially increasing the number of carriers that have enough kinetic energy to make it over that potential barrier. Okay, so it's all related to that exponential distribution of electrons in the conduction band and the exponential distribution of holes in the valence band. Okay, so when you change the barrier height by applying a bias, you're exponentially tuning the diffusion current. You're actually not even. What do you think you're doing to the drift current? Just curious. What do you think is happening to the drift current when you change the applied bias? What do you think? Smaller? Do you think it's getting smaller? So let's say if the barrier is smaller, do you think there'll be less drift current? It actually doesn't change much because it turns out that the rate limiting step for diffusion is the rate at which minority carriers make it to the depletion region. So as soon as they make it to the depletion region, they're swept across, and you sort of have to wait a while for another minority carrier to wander in and get swept across. So it turns out that the rate at which minority carriers drift across a junction really isn't dependent on, ideally, on the magnitude of the electric field in the depletion region. So this current here is due to, under reverse bias, is due to minority carrier drift. Oops. And it's not really too strong of a function of applied reverse bias. Because it doesn't matter really how much voltage you drop across the junction, you're still just going to collect minority carriers at pretty much a constant rate. Okay? And that's dictated by the rate at which they diffuse into the depletion region. Okay, on the other hand, you have exponential dependence of current in the forward bias regime because it's now dominated by majority carrier diffusion across the junction. Oops. Across the junction. I'm going to, okay. Across the junction. Okay, got it. So qualitatively, does this make sense? All right, so just keep that in mind as we go through and develop the current versus voltage analytical equations. Okay, so what happens to the majority carriers when they diffuse across the junction? Okay, so let's look at the electrons on the right. You know, a lot of them on the right, because of concentration gradient, they want to diffuse to the left. If you lower the potential barrier by applying a forward bias, you allow a lot of them to diffuse. What do they become when they reach the p side? In other words, are they still majority carriers on the p side? No. So they suddenly see all these holes when they exit the depletion region and enter the p, the quasi-neutral p side. They see a lot of holes. So what happens when an electron meets up with a hole? it dies, right? It gets annihilated. Very good. So what will happen is that if you look at this concentration of electrons, let's just say excess electrons. So when electrons diffuse from the right to the left, they're sort of extra, right? These are not the electrons that normally would exist under equilibrium conditions. There's some excess electrons introduced due to diffusion from the right, the end side. So we have excess electron concentration, and because of recombination, it's going to just exponentially decay with distance. Okay? So on the end side, you have excess holes. And the concentration of holes will also die out exponentially with distance. Okay? So remember, I think maybe we went over an example when we talked about non-equilibrium or generation recombination. So remind me, fundamentally, why do these profiles, why are they exponentially decaying functions? Distance. Okay, so because the rate at which they are annihilated is proportional to what? To their own concentration, right? The rate at which the excess carrier concentrations die out is proportional to the concentration of excess carrier concentrations. So any function that is whose derivative is proportional to itself is an exponential function. Okay. Yes, Lewis. Good question. So how long does it take for these carriers to die out? I mean, what's the typical distance at which they die out? Right, so it's actually the diffusion length. Right, so I'm sort of exaggerating here, but this is the depletion region, okay? And we're talking about the edge of the depletion region now. So once the majority carriers diffuse across the junction and they exit the depletion region, then they become minority carriers. They see all these majority carriers and they start dying out. So the characteristic distance, where this falls by 1 over E, is the diffusion length. So there's the minority carrier diffusion length. So on the right and the end side, the average distance that a hole goes before it is annihilated due to recombination is L sub p, and that's the square root of dp tau p. Right? And then same thing on the left. Electrons, they probably have usually higher mobility for the same comparable doping. But anyways, the average distance before an electron gets annihilated is the electron diffusion length on the p-type side. Okay? So within a few diffusion lengths, pretty much this concentration goes to 0. This excess minority carrier concentration goes to 0. So this terminology is a little bit confusing, but we call this forward bias. We refer to that as minority carrier injection. Okay, because we're injecting excess minority carriers, which are electrons, on the p side, quasi-neutral p side, outside of the depletion region. And we're injecting excess holes into the n side, outside of the depletion region. So the terminology is minority carrier injection. That's what happens under forward bias. Now this is in contrast with reverse bias, where we're actually collecting minority carriers. So minority carriers are actually collected across the junction to the side where they become majority carriers again for drift. Right? So under reverse bias, the dominant process is minority carrier collection back to the size of majority concentration. But under forward bias, we call it minority carrier injection. And that's due to majority carrier diffusion across the junction. Right? So I hope you don't get confused. Okay. All right, so now let's derive the current versus voltage equation. So you can see, indeed, that the current increases exponentially like this. And so you can figure out what the pre-exponential term is as well. OK, so we're going to go through a very simple analysis, assuming that both sides are not degenerately doped. And the reason why we're assuming it's not degenerately doped is because we want to be able to use the Boltzmann approximation. Right? Just use a simple exponential relationship between the Fermi level and the carrier concentrations. Steady state means that nothing is changing with time. Okay, so when you apply a bias, some current will steadily flow. Okay, so this means that nothing is changing with time. So the carrier concentrations are not changing with time. Okay, the next condition or assumption is low-level injection. So I should mention, maybe it's not obvious, but so there's a depletion region right at the junction. The N-type and P-type sides are depleted of mobile carriers, so we call that depletion region. But outside of the depletion region, we assume that the net charge density is 0. So we refer to those regions as the quasi-neutral regions. Okay? All right, so now we're assuming that the excess minority carriers introduced into the quasi-neutral regions is not that high. So this is the low-level injection conditions. So what does that mean? That means that, well, what does it mean? It means that N on the N side, the electron concentration on the N side is not really affected, right? The majority carrier concentrations are not significantly affected under low-level injection conditions. So that means the electron concentration on the N side is approximately equal to ND. Oops, well, technically, hold on. Not, okay, so N naught means the equilibrium concentration of electrons on the N side. Okay, and so this is equal to ND. Okay, on the P side, in the quasi-neutral P region, the whole concentration in the quasi-neutral P region is going to be equal to the, approximately equal to the equilibrium concentration, which is dictated by the dopant concentration. Okay? All right, the final assumption we're going to make is that in the depletion region, we're going to assume that it's kind of relatively small, so carriers diffuse across it, and because the concentration of electrons and holes is a little bit lower. I mean, it's lower than the dopant concentrations for sure, but the concentration of electrons and holes is relatively small, and the distance is relatively narrow, so that no recombination or no significant generation occurs in the depletion region. Okay, so that's a simplifying assumption. So this means that whatever electrons are diffusing from the N side to the P side, none of them will die out in the depletion region. Same thing, holes diffusing from P side into the N side, as they cross the depletion region, they're not going to die out. So in other words, the electron current density is not going to change as a function of distance in the depletion region, and the whole current density will not change either in the depletion region only. Okay? Okay, so let's sketch. I think I did this already with computer, but so remember, the total current flowing in a semiconductor can be due to electron components and hole components, and each of those can have drift and diffusion components. So these equations are shown here are complete in that you have electron, right, diffusion, current density. Okay, this is current density, and you have hole current density equations here. So that you have both drift and you have diffusion components for each of the whole electron and hole currents. Okay, so remember that N is defined to, sorry, that's not a good N. Usually we just keep track of the excess carrier concentrations. So just remember that the carrier concentrations are just equal to their equilibrium values plus the excess concentration. So this is convenient because if we're taking the derivative of the carrier concentration, it's really the same as the derivative of the excess carrier concentration, right? The equilibrium value is a constant, so that drops out. So that's the only thing we do, over here. It's just better, it's just easier to keep track of the excess carrier concentrations. Okay. So for an example, let's do an example of how, so the current density flowing in your diode is going to be the same no matter where, if you're looking at the in the P region, in the depletion region, or the N region, right? It's the same current that flows through the entire diode structure. So that's why J is drawn to be a constant value here on this plot. Okay, so we know that there's going to be some current due to electrons diffusing across the junction. So electrons, due to the concentration gradient in the lowered barrier, potential barrier, counteracting that. So electrons are going to diffuse from the right N-type region through the depletion region and reach the P-type quasi-neutral region. And they'll die out exponentially, right? So the diffusion current, so electron diffusion current is going to die out exponentially inside the P-type region. Okay? Now remember, we're assuming that whatever electrons start diffusing into the depletion region, none of them are lost due to recombination. So that's why this line is at a constant level in the depletion region. Okay, now the total current is J sub n plus J sub p. So if J, the total current density, is equal to J, and if we know Jn should look like this, then we know, oops, Jp should look like that, right? It's just basically the sum of B has to equal to J throughout. Okay. All right, now then we can just fill the rest of this out. So the whole diffusion current in the depletion region has to exactly, total up to has to be such that the total adds up to the total, J. Okay, and then on the P side, we know that the holes will die out due to recombination. So the minority carrier diffusion current due to holes is going to die out exponentially with distance as well, to 0. And again, since the total has to equal J, we know that the electron current component has to look like this on the N side. Make sense? So qualitatively, you're introducing, okay. Let's look at the p-n junction. And in practice, there are metal contacts at each side. And you're applying a bias like this to allow current to flow. So let's say a current density to flow like this. Okay. So remember metal semiconductor contact. What kind of carriers flow, let's say, on this side at this p-type contact? What's happening physically there? Are electrons or holes, or what's going in and out of that contact? Remember, what kind of carriers flow in a metal semiconductor contact? Majority, right? Are you going to say majority, Bjorn? Okay, so what happens is that holes flow into this metal semiconductor contact on the P side, and electrons, flow in to the metal semiconductor contact on the N side. Does that make sense? Okay, so electrons that are negatively charged, that they're flowing in the negative x direction, that's contributing current. So electrons are supplied by the metal semiconductor contact. They come in, they're majority carriers, but some of them die out due to recombination with holes. And whatever survives, or whatever's left over, will just diffuse across the barrier and recombine on the other side. Okay, so I had shown diode, light-emitting diode before. So what's happening in these quasi-neutral regions again? Just remind me. Recombination. What happens when electron and hole recombine? Well, they die, but some energy is given off, right? So in 3-5 semiconductor materials, the energy is given off as light. So in the light-emitting diode, basically works like this. You forward bias it, and due to recombination in these regions, you give off light. So the more current you flow due to higher bias, the more intense the light is. Yes? Okay, so your question is, why do the electrons recombine quickly? This is just a cartoon. So the average distance that it takes for the electron current density to diffusion current density to die out is actually related to the diffusion length. So it really depends on the mobility, which is related to the dopant concentration, and the minority carrier lifetime. The lifetime is related to how many crystalline defects or like metallic impurities are in the n-type side. Sorry, the p-type side. Oh, okay. So you're asking why the electrons die out so quickly? Yeah. Okay, it's because you're losing electrons due to recombination with the holes. Right. So some of the electrons that are supplied by the metal contact end up recombining with holes on the n side. The other ones end up recombining with holes on the p-type side. Question. Great question. Why is Jn lower than Jp in this particular qualitative example? P plus n, that's right. So if the p side is doped more heavily than the n side, then most of the current flowing across the junction is due to hole diffusion across, right? Because you have more concentration gradient, or yeah, exactly. Normal PN. Right, so if the P and if ND and NA were equal, then yes, it would be matched exactly in the middle. You're right. But in reality, in an integrated circuit device, you always have one side that's doped much more heavily than the other, right? But that's absolutely right. But that's an important detail, because sometimes I might give you a plot like this on a test and ask you, okay, is this P plus, which side is more heavily doped? And you should be able to tell based on which current, electron or hole current is dominant. That's a good question. Okay, so the rest is just math, okay, that we're going to go through today. But essentially, remember, J is equal to the electron and hole components added together throughout. And so since we assumed that Jn and Jp are completely flat in the depletion region, all we need to do is figure out Jn. Let's see. Let's do this. And so electron diffusion current at the edge of the depletion region on the p side. So Jn at minus xp. And we can figure out what Jp is at x equals xn. If we can derive equations for these two values of current, we can add them together, and that will give us the total diode current. Okay, so that's all we're going to do in the next few slides. Okay, does that make sense? So basically, yeah, we're just going to derive equations for the minority carrier diffusion currents on both the p side and the n side, evaluate them at the edge of the depletion region, and then add those results together, and that's it. Okay, so that's outlined here on this slide. So we basically want to solve the minority carrier diffusion equations to get, so if we get the excess carrier concentrations as a function of x, then we can take the derivative to find the current density as a function of distance in the quasi-neutral regions, and then we can evaluate at the edge of the depletion region, p side and n side, and add it together. Okay. Now we're assuming here, next time we're not going to assume it's infinitely long n-type and p-type sides, but for today we'll assume that it's infinitely long on both n and p sides, so we have enough distance for electron and hole concentrations to die out due to recombination. So at either plus infinity on the right or negative infinity to the left, we expect the excess carrier concentrations to die out to zero. Okay? So really the tough part for today is figuring out what is the excess carrier concentration, what are the excess minority carrier concentrations at the edge of the depletion region. Okay. Well, let's first find out what the equilibrium concentrations are, and then we worry about what happens when we apply a voltage. Okay, so in equilibrium, you have Pn equals Ni squared. And we know that the majority carriers are defined by, the concentration of majority carriers is dictated by the doping. Okay, so the equilibrium hole concentration is equal to Na on the p side, and the equilibrium electron concentration is equal to nd on the n side. And therefore, you get the minority carrier equilibrium concentrations, just ni squared divided by the majority carrier concentrations. Now, as I mentioned, we're assuming low-level injections. So even if we apply a bias, we're going to assume that the majority carriers are not going to change from the equilibrium values. So they're just going to continue to be determined by the dopant concentrations on either side. Okay? So that means that the only thing that changes with bias, right, with injection of minority carriers, is the minority carrier concentration. Okay? All right, so this might seem a little confusing, but do you remember the relationship? Okay, I think it was covered by Newell. If you change, if you change the position of the Fermi level linearly, how does the concentration of the carriers change? Exponentially, right? Great. So by applying a bias, what you're doing is you're actually sort of linearly moving like the potential barrier, or you're basically moving the Fermi level linearly with the bias. So you would expect the carrier concentration to change exponentially with the bias, right? And that's consistent with what we talked about earlier today, that the number of carriers that can diffuse across a potential barrier is going to be exponentially dependent on that potential barrier height. Okay, so it turns out it can be shown that, okay, so in the depletion region, it's not at equilibrium. Okay, but in the quasi-neutral p side and the quasi-neutral n side, we can sort of assume that they're approximately at equilibrium. Okay, so let's review. Why is that a reasonable assumption that the quasi-neutral regions are? We can draw a normal Fermi level, a Fermi band diagram with one Fermi level for both the p side and the n side in the quasi-neutral regions. Why is that reasonable? Huh? You can't see the junction. That's right. So what you mean probably is that there's really negligible electric field. Right? There's like we're assuming for now no light shining on this in the quasi-neutral regions. The electric field is relatively low in the quasi-neutral regions compared to the electric field in the depletion region. So this is why we can draw a energy band diagram both on the p side with a single Fermi level on the p side, and we can also draw a single energy band diagram for the quasi-neutral n side with a single Fermi level on the n side. But in the depletion region, you have an electric field, so it's clearly not in equilibrium. We know the p-n product should not be equal to ni squared. But it can actually be shown that these the Fermi levels for the carriers don't change too much throughout the depletion region. Okay? So we can actually draw them sort of flat, like this, except now they become quasi-Fermi levels, right? Because they're not in equilibrium. Okay, so you have one quasi-neutral electron quasi-Fermi level, okay, and you use that to determine the concentration of electrons, and you have a separate quasi-Fermi level that will help you track the concentration of holes. And then somewhere out here, they end up merging, right? Near the edge of the depletion region, these quasi-Fermi levels will merge together into one again when you reach the edge of the depletion region, because those are, the NP product once again becomes Ni squared in the quasi-neutral regions. Okay, so inside the depletion region, we can have an approximation. There's going to be a separation of the quasi-Fermi levels for electrons and holes. So what does this mean? The concentration of electrons and holes, well, the product, what does it mean for the product? It means that the concentration of the product is going to increase. Okay, well, actually, let's just put it this way. If you just do the math, if you just wanted to write equations, you can express, I mean, this is from before. Hole concentration is related to the quasi-Fermi level exponentially. The electron concentration is related to the quasi-Fermi level for electrons exponentially. You take the p-n product, and you find as Ni squared, but modified by this exponential term. And remember I mentioned at the beginning of class the splitting in the Fermi levels? that represents the applied bias. Okay, so this distance here is Q times VA. So bottom line is the carrier concentration, more precisely, product of P and N is enhanced exponentially by the applied bias. Yes, question? Oh, okay. Yes, that's right. This is a coincidence that EFN sort of lines up with EI on the left, and EFP lines up with EI on the right. That's right. That's a coincidence. Good question. Okay, so we'll work through the math, but then qualitatively you'll see this makes sense. So on the N side, remember we're assuming that the majority, the P side, the majority carrier concentration is not changing. So that exponential factor, enhancing the PN product, really affects only the minority carrier concentration. Right? So if the whole concentration on the left is not changing, but the PN product is enhanced, then that means N must be enhanced. Okay? So, so N on the P side is equal to the equilibrium concentration plus the excess. Wait, hold on. Yeah, right. Plus the excess concentration. So that means that delta NP is equal to NP minus NP naught. I went through that because that explains why you have this -1 over here. Okay? So the equilibrium concentration is Ni squared over Na. You have to subtract that to get, from the carrier concentration to get the excess carrier concentration. Okay? Any questions on how we derive this equation for the excess electron concentration on the P side, at the edge of the depletion region? So remember, this only holds at the edge of the depletion region because the law of the junction holds throughout the depletion region. It does not hold outside of the depletion region. Okay, we can do the same thing for the N side. Okay, the N doesn't change. The concentration of electrons doesn't change on the N side because it's low-level injection. But we know the PN product is enhanced exponentially. So that means the P is enhanced exponentially. So that enhancement is in P, so you have to subtract out the equilibrium concentration to get the excess whole concentration. Okay? Does that make sense? All right, so fundamentally then, if you plot on a log scale, okay, the reason we have to plot the carrier concentrations on a log scale is because it's orders of magnitude difference between the electron and hole concentrations on each side. So we have the P side on the left, right? So you have, hole concentration higher than the electron concentration, and the N side on the right. So the electron concentration is greater than the hole concentration. Which side is more heavily doped? P side, because the hole concentration is greater on the left. The majority carrier concentration is greater on the left, the P side, than the right, and than the N side. Okay, good. Now, so on a log scale, we can see that at the edge of the depletion region, the minority carrier concentration is enhanced exponentially due to minority carrier injection. What is this distance here? Yeah, it represents e to the q VA over KT. So in this case, it's a few orders of magnitude, 5 orders of magnitude, roughly, let's say. Notice that that distance is the same as this distance here, right? Because on both sides of the junction, the minority carrier concentration at the edge of the depletion region is enhanced by e to the q VA over KT. Okay, so can somebody explain qualitatively why does it make sense that the carriers that diffuse across the junction, the carrier concentration is enhanced exponentially? That's actually redundant with the question I asked earlier in the lecture, but yes? That's true. But more importantly, what does it do to the barrier to diffusion, the potential barrier to diffusion? That's right. So you get exponentially more carriers that can diffuse across the junction. So that's why you have exponentially more minority carriers on each side, because when the carriers diffuse across, they become minority carriers. Right? So hopefully qualitatively this makes sense. So the concentration of carriers at the edge of the depletion region, minority carriers, is enhanced exponentially with the applied bias. Now the distance over which the carriers die out to their equilibrium value is going to depend on the diffusion length. Right? So in this particular cartoon, it looks like the diffusion lengths are comparable, okay, on the left and on the p side and n side. But basically, this distance here is proportional to L sub p, the diffusion length for holes on the n side. And this distance there is going to be proportional to L sub n. Okay, so if somebody were to show you this plot of carrier concentrations as a function of distance in a p-n junction, you should immediately be able to tell that that is a forward biased junction, right? Because a forward bias reduces the potential barrier to diffusion. You get enhanced carrier flow across the junction. So I'm going to skip ahead to explain that, in contrast, in reverse bias, you actually don't see an enhancement of minority carrier concentration on the left and right sides. Outside, in the quasi-neutral regions, you have carriers actually are depleted from the edges of the depletion region. Okay, so qualitatively, if somebody were to show you carrier concentrations, you should be able to tell us if it's at equilibrium or forward bias or reverse bias. Okay. Why are minority carriers depleted from the edge of the depletion region under reverse bias? They don't want to cross the other side? Not really. Okay, wait. So remember, minority carriers, if they actually reach the edge of the depletion region, they want to go across. Right? So any minority carriers that want to, reach the depletion region, they want to go across. So basically, the depletion region will actually suck up, minority carriers from both sides. So that's why you have this concentration gradient, sort of driving minority carrier diffusion to the depletion region. But anyway, okay, we'll cover that again in a few minutes. So let's get back to the math, unfortunately. Okay, well, let's do a simple example. If you have a p side that's doped 100 times more heavily than the n side, 10 to the 18, what are and let's say for a forward bias of 0.6 volts. Let's see how, I think almost all of you actually got this correct on the first quiz, which is great. So what do you think e to the q VA over kt is? Based on what you know, that kt over q log 10 is 0.06 volts. Okay, sorry. Right, so VA is 10 times greater than 60 millivolts, so you got 10 orders of magnitude difference here. Okay, so if you apply a forward bias of 0.6 volts, that means you're enhancing some carrier concentration by 10 orders of magnitude. That make sense? Okay, so on the n side, okay, so let's say on the p side, let's do the p side. The minority carrier concentration in equilibrium is what? 10 to 2, very good. So that means n on the p side is np naught plus delta np equals 10 to the 2 plus what? 10 to 12. So it's basically 10 to the 12. Let me just make sure that's right. That should be trivial, right? Yeah, that's no problem. Okay, good. N side, let's do the n side. The minority carrier concentration is holes. On the n side, at equilibrium, it's equal. What is it equal to? 10 to the 4, excellent. Okay, so now not in equilibrium, we have the equilibrium value plus the excess concentration. So it's 10 to the 4 plus 10 to the 14. So it's about 10 to the 14 per centimeter cubed. Okay, so notice, actually in reality, due to charge neutrality in the quasi-neutral regions, the excess majority carrier concentrations actually also equal the excess minority carrier concentrations, because the net charge has to be 0, right? It just turns out, okay, just as a quick example, like this is equal to delta n on the n side, right? For charge neutrality, the excess holes you introduce have to be matched by the excess electrons. So the extra electrons come in from the metal contact to match this up, so match the concentration profiles so that you get, charge neutral material on the n side outside of the depletion region. But see, this change in electron concentration is also 10 to the 14, but it's much less than 10 to the 16. So that's why this is why we call it low-level injection. The majority carrier concentrations are not significantly affected. It's really only the minority carrier concentrations that are affected. Okay. Okay, so what are the excess minority carrier concentrations at the edge of the depletion region? Oh, hold on. I did this kind of backwards. Okay, so from the law of the junction, the carrier concentration, hold on. So it should have been like this. Let me write the proper way. So NP is equal to NP naught e to the q VA over KT. Okay? So this is 10 to the 12. So this is still correct. It's just that now what I wanted to do here is that to point out that, remember, for keeping track of diffusion current, all we care about is the excess carrier concentration. So delta NP is equal to NP minus NP naught. So this is still 10 to the 12 minus 10 to the 2, which is equal still 10 to the 12 per centimeter cubed. Okay? All right, so what I should have done here was P sub n is equal to the equilibrium concentration times e to the q VA over KT, which is equal to 10 to the 14 per centimeter cubed. Right, so then the excess hole concentration on the n side is equal to concentration minus the equilibrium concentration. So it's 10 to the 14 minus 10 to the 4. Is that right? So it's 10 to the 14. But bottom line is really the minority carrier concentrations are just going to be equal to the excess minority carrier concentrations. Okay. And the fundamental reason for that is because this under some reasonable forward bias voltage that we use for a diode, this exponential term is typically way, orders of magnitude greater than 1. Okay. Okay, so now we have the boundary conditions. We know what the excess minority carrier concentrations are at the edge of the depletion region are. We know what they are away from the depletion region. They go to 0. So now let's just solve the minority carrier diffusion equation to find the solution, apply the general solution, apply the boundary conditions, and get the actual particular solution for the excess minority carrier concentrations in the quasi-neutral regions. Okay, so as we just derived, this is the excess carrier concentration at the edge of the depletion region on the n side. And we know that far away from the depletion region goes to 0. The minority carrier diffusion equation is written here. We have no generation, no generation of electron hole pairs due to light. And we have nothing changing with time at steady state. So the only terms left in the minority carrier diffusion equation are just the recombination term and the diffusion term. So you end up with a nice, simple second-order differential equation. And the general solution is just going, we know any function whose second derivative is proportional to itself is also an exponential function. So it can be exponentially increasing or exponentially decreasing function, right? So you have this is the general solution. We solve for A1 and A2 by applying these two boundary conditions. Okay. So does anybody remember what are the conditions under which the minority carrier diffusion equation can be used? I mean, why can we apply the minority carrier diffusion equations, or why do the minority carrier diffusion equations hold in the quasi-neutral regions? Low-level injection. Okay, there was one other assumption for the minority carrier diffusion equation. Negative. Well, how can current flow? There's two ways: diffusion and drift. Okay, what are we ignoring here? Drift. And that's because the electric field is small in the quasi-neutral regions compared to the depletion region. So that's why. So all the assumptions for reducing the continuity equation into a minority carrier diffusion equation hold. Okay, so that's why we can apply the minority carrier diffusion equation only in the quasi-neutral regions and only for minority carriers. We cannot write it for majority carriers, because even if the electric field is small in the quasi-neutral region, the concentration of majority carriers is very high. So we can't neglect the drift current for majority carriers. But for minority carriers, we can assume that the drift component of current is negligible. Okay, so that's why we can apply the minority carrier diffusion equation in the quasi-neutral regions. Okay, so that's the same general equation or general solution. And so we can apply the boundary conditions. And not surprisingly, it's a very simple result. The excess concentration of electron holes on the n side, starting from the edge of the n-type region, just dies out exponentially with distance. So this is proportional to e to the minus x over LP. Right? So that's basically the solution. Oh, okay, so notice this is x prime LP. So just for convenience, x prime is defined to be x minus xn. Right? So x prime is defined to be 0 at x equals xn. Right? So it's just you start from some constant dictated by the law of the junction and decays exponentially. And then for electrons on the p side, again, it's just convenient to define this exponential function like this. So this is x equals minus xp, but we define this x double prime as going, pointing in the negative x direction. So let's go back. See, so here's x double prime. We define x double prime to be 0 at the edge of the depletion region on the p side, and it increases as you go deeper into the p side. Okay, it just makes it easier to write the equation. Okay? So simple exponential decaying curves. Qualitatively, that's exactly what you expected, right? I hope. Okay. Okay, so now we can take the derivative, right, to get the diffusion current. Because remember, we just want to find the minority carrier diffusion current and evaluate it at the edge of the depletion region. So now we can get an expression for the diffusion current, the minority carrier diffusion current, by just using, taking the derivative and multiplying by q and at q times the diffusivity or diffusion coefficient. Okay. So that's pretty straightforward. That's all that's done here. Then finally, we evaluate the minority carrier diffusion components at the edges of the depletion region. So that means at x double prime is 0 and at x prime is 0. Okay, so these exponential terms go to 1. So you end up with these terms. They have this exponential e to the qVA over kt minus 1. So you can group them together. So you end up with this equation. And of course, the diode equation, as you expect, is increases exponentially with VA positive. If VA is positive, then this exponential term is much greater than 1. If VA is negative, this exponential term is negligible compared to 1, and you just get some negative constant current flowing. So this equation then gives you the the value of current, this pre-exponential factor. Okay, and so that's the ideal diode equation. Usually it's written as in terms of current, not current density. So you have to multiply it by the area, right? So this is the junction area A. Okay. Any questions just qualitatively or even quantitatively about how we derive the ideal diode equation? All right, so notice this says 60 millivolts per decade. Does that sort of make sense that the slope would be 60 millivolts per decade? In other words, if you change the applied bias by 60 millivolts, you're changing the number of carriers that can diffuse across the junction by a factor of 10, by 1 decade. I hope that's consistent with what 60 millivolts corresponds to 1. Yeah, well, it's right. I mean, it's consistent with kT over Q times the natural log of 10 is equal to 60 millivolts, right? But if you want to do it as an exercise, you can actually go through this and say, well, okay, if we want to look at a current like I2 at a voltage V2, and then we want to look, it's a useful exercise maybe, at another current I1 corresponding to a voltage V1. Basically, what this is saying is that if I2 over I1 is equal to 10, then V2 minus V1 is equal to 60 millivolts. That's what it means. So this inverse slope, sorry, this should actually be inverse slope, right? And this is plotted on a logarithmic scale. Right? So that's why it looks like a straight line, because you're plotting the log base 10 of the current on the right side versus the applied bias on a linear scale. Yes? Okay, so this is a plot from Professor Hu's book showing, actually it's measured data. So comparing the ideal, which is the blue curve, with some measured data. So we'll talk about non-idealities in next week, actually. Yeah. So why, in reality, a real diode doesn't exactly follow this ideal diode equation. That's why it's called ideal diode equation. But yes, Andrew.
So right at the point where it's
Okay, so the question is essentially, is that where this 1 starts to become significant? Yeah. I don't think so. Actually, yeah, because this is 0.4 volts, right? So still e to the, this is VA over KT over Q, essentially. So 0.4 is still much greater than 60 millivolts. So it turns out, and we'll cover this next time, is that there's an extra source of current that flows under forward bias. And that's why you start to see this extra hump. That extra source of current, this is a log scale, is not big compared to like a normal, strongly turned on diode. But if you try to operate the diode with very low current, then that extra current component starts to become significant and dominates the diode current. Can somebody guess what that extra source of current would be? How can you get more current, more carriers to flow across the junction under forward bias? Let's go back to look at the forward bias. It has to do with something with generation recombination. Yes? That's right. So something's happening in the depletion region. Now, what would have to happen net in the depletion? Net generation or net recombination to provide extra current flowing? Net generation. That's right. So if you have an electron and hole pair generated in the depletion region, electrons will want to move to the right, drift to the right, and holes will want to drift to the left. So wait a minute, that's not right. Wait. Electrons go to the right. That's like negative current. It's recombination. Yeah, right. It's net recombination. Yes. So the answer is net recombination in the depletion region. So this assumption here that a current actually stays flat is not true. You actually do get some recombination of carriers, so it dies out a little bit here before it comes out. So what that means is that you actually need to supply extra electrons and extra holes, not only to recombine in the quasi-neutral regions, but also and to diffuse across the junction, but also to recombine in the depletion region. Right? So it's net recombination in the depletion region that creates this extra current in the for low bias. I mean, so that always exists. Okay, it's just that it doesn't become significant unless you have low bias. Right? Okay, very good. Okay, so let's look closely at that diode saturation current. So this, if you notice, has this dopant concentration value in there. And the doping in a p-n junction diode can actually vary over a wide range, like from 10 to the 15 up to 10 to the 20. So that tells you that the I naught can change quite a bit by orders of magnitude. Okay, what else can actually change over many orders of magnitude in the diode saturation current? Okay, what if I allow you to change the material? Like for a light emitting diode, is it like 3,5 semiconductor? What else would change significantly? Huh? Intrinsic, very good. Because the energy band gap can be different. So the intrinsic carrier concentration also can change by orders of magnitude depending on the energy band gap of the material. So that's just something to keep in mind, that I naught, which is equal to A times J naught, can change over orders of magnitude. But fortunately, most of the time, you don't have to remember that entire whole equation. You only have to remember like one side, okay? Because, like I said, usually one side is much more heavily doped than the other. And okay, the diffusivities, differences between electrons and holes and diffusion lengths aren't going to change by orders of magnitude. So if you have a huge difference in dopant concentration for n-type and p-type side, usually you have to be careful. Usually one of these terms, only one of these terms in I naught is going to be dominant. So like on a quiz, you can probably figure out, okay, you only need to calculate one of those fractions to estimate the I naught. Okay? Okay, so if I didn't allow you to use notes, how would you remember this I naught equation? Let me explain to you. So we know that current is due to, let's say forward bias current is due to what? It's due to diffusion of carriers across the junction. And that current is going to be related to this exponentially, I mean, that current, the carrier concentration will decay exponentially. And so the current density will be exponentially decaying. And that depends on the diffusion length and so on. Okay, so sorry, I'm rambling. So basically, the current flowing across the junction is due to diffusion. Okay, so now we have diffusion of, let's say, holes across the junction. So that's d sub p. And the diffusion current is proportional to the diffusion coefficient, right? How about the gradient, the concentration gradient? Is that going to, how does that depend on the diffusion length? If the diffusion length is shorter, then the carriers die out more quickly. So you have a steeper concentration gradient. So you have L sub p in the denominator, right? So d sub p in the numerator, this is the whole diffusion term. So d sub p in the numerator, L sub p in the denominator. Okay? Then the number or the concentration of minority carriers depends on the equilibrium concentration, right? So that's Ni squared over Nd for holes on the N side, right? And current is charged as a function of time, so you know there's a Q there, okay? And the current is proportional to the area of the junction, so you know that there's an A there. Okay, so you can easily, I hope, figure out that, yes, the diffusion term, for I naught associated with holes is going to be proportional to the LP, inversely proportional to the LP. It's going to be proportional to Ni squared over Nd, because that's the equilibrium concentration of holes on the N side. And you have to multiply by Q and A. Okay? And you can do the same kind of derivation for the term corresponding to, see, so this term here, where's my pen? Okay, this term here on the right corresponds to diffusion of electrons into the quasi-neutral p side. Okay, so you have current due to diffusion of holes on the N side, diffusion due to electrons in the p side. Does that make sense? Okay, so hopefully it's easy for you to remember this. Okay, now it turns out that there's another way you can remember I naught. So let me just quickly do that. As I mentioned, the concentration of, okay, so what happens under reverse bias? Okay, under reverse bias, okay, you have hardly any majority carriers diffusing across the junction because the barrier is just too high. Okay, so exponentially, very few electrons and holes can diffuse across the junction due to the concentration gradient. So the only current, the dominant component of current is just due to drift of minority carriers across the junction. So as I mentioned, any holes that on the N side that wander into the depletion region will get swept across, and any electrons on the P side that wander into the depletion region will get swept across. So you'll end up you'll deplete minority carriers from the edges of the depletion from the edges of the neutral regions. Okay, so that's why you have a decreasing concentration of minority carriers towards the depletion region. So now you get diffusion of minority carriers in the reverse bias state. You get diffusion of minority carriers to the depletion region. So towards the depletion region. Why is it diffusion? Okay, so because there's a concentration gradient, right? So any minority carriers that reach the depletion region are immediately swept across. So it's like, oh, you're missing. So now it's like one less electron or hole on the N side. So it's like, okay, there's concentration gradient now. So in steady state, you have this profile where minority carriers, this is under reverse bias, minority carriers are just depleted from the edges of the quasi-neutral regions because they're swept across the depletion region when they reach there. So there's actually a concentration gradient. So minority carriers diffuse under reverse bias towards the depletion region. Once they reach the depletion region, they flow across by drift. Okay? But the rate at which carriers drift across the junction under reverse bias is limited by the rate at which they can be supplied by diffusion. Okay? So even though it's drift current, it's actually limited by a diffusion process. And that diffusion, so where do the minority carriers come from? Remember I mentioned, okay, here's the P N junction. Only holes, okay, only majority carriers flow in and out of a metal contact. So only holes flow in and out of this P side, and only electrons flow in and out of the N side. Okay, so how are you going to get holes supplying this diffusion to drift across the junction? It's generation, right? So basically, you have to wait for them to be thermally generated, and there's always constant, thermal generation and recombination. But okay, net. So you have to wait for them to be thermally generated within this region, within one diffusion length of the depletion region. Okay, so basically, the rate at which you can generate thermally minority carriers to supply this drift current, that's going to limit I0. Okay, this is under reverse bias. So how do we do this? Okay, so the rate, remember this is the rate at which we have recombination or generation is proportional to the excess concentration divided by the lifetime. But now the excess concentration is negative, right? Because we're depleting the minority carriers. So we have negative delta NP and negative PN, in the quasi-neutral regions. So so now we can use a depletion approximation for the minority carriers. So just to derive this I naught. So the depletion approximation for minority carrier concentration under reverse bias is like this. We can assume that within one diffusion length, we have 0 minority carriers. And this is a rough approximation. And then after that, we assume that there's no depletion of minority carriers. Okay? So within this region, what is delta P on the n side? It's just equal to Ni squared over Nd. Because the equilibrium concentration is Ni squared over Nd. And we're assuming that's 0. So the excess, is minus Ni squared over Nd. Okay, so we can have the same, this depletion approximation for minority carriers on the n side and on the p side. And okay, so we take the excess carrier concentrations, divide by the minority carrier lifetime, and that will be the rate at which we can thermally generate the excess minority carrier concentrations within one diffusion length. Okay, so you have to then multiply this is happening all throughout the diffusion. This depletion region is LP long on the n side, and an LN long depletion region on the p side. Okay, so you basically end up adding these two components of current together. Okay, the rate at which minority carriers are generated within one diffusion length in the quasi-neutral regions on either side of the depletion region. Add them together, and it turns out that you get the same equation for I naught as before. But this is assuming that you know that, okay, remember LP is equal to square root of dp tau p. So this means that LP squared is equal to dp tau p. So this means that LP over tau p is equal to dp over LP. Right, so if you actually take advantage of this relationship, and notice we have LP over tau p here, just substitute dp over LP, you'll see that this is the exact same term that we derived before. You can do the same thing for the first term. So basically, you can see that this equation for I naught is exactly the same as the equation we derived under forward bias conditions. Okay? So just to summarize then, this current that flows, so when VA is negative, really you just have minus, this is minus I naught if VA is much, much less than 0, right, under reverse bias. Okay? Does that make sense? Okay, so I think qualitatively, that's basically it. Okay? All right, let's move on to the social hour. If you have any questions, I'm happy to answer at the beginning of the next lecture. All right.